Welcome back. This is Spectre P, and we are Spectre AI. This video examines a simple but dangerous idea. Modern exploits don't usually fail because attackers can't execute payloads. They fail because attackers make too many mistakes before they get it right. In late 2025, a critical command injection vulnerability in FortiSIEM showed how fragile that margin really is. Even after years of hardening, filtering, and monitoring, a small space of valid inputs still existed where a single correct command could pass validation and lead to full compromise. Traditionally, attackers have to find that space through repeated trial and error, generating logs, anomalies, and detection signals along the way. What changes in a quantum threat model is not the payload, not the exploit mechanics, and not the vulnerability itself, but the economics of guessing. Quantum-assisted search compresses uncertainty, reducing the number of failed attempts required before success, shrinking exposure windows, and lowering the observable footprint that defenders rely on for early warning. The result is not a louder attack, but a quieter one, where fewer mistakes mean fewer alerts and faster compromise. This analysis is not about deploying exploits or bypassing patches, but about understanding how emerging computational capabilities alter attacker certainty long before cryptography is touched. The full technical breakdown, including mathematical modeling and executable simulations, is provided in the companion materials. Please look in the description for a GitHub link for code and detailed PDF. Modern security systems are built around a quiet assumption that attackers will fail many times before they succeed. Detection logic, logging pipelines, anomaly scoring, and alert thresholds all depend on this idea. An attacker is expected to make repeated incorrect attempts, generate malformed inputs, trigger validation errors, and leave behind a trail of evidence long before anything meaningful happens. In practice, security tools are not designed to catch success directly. They are designed to catch accumulation of mistakes. Each failed attempt increases noise, raises suspicion, and pushes activity closer to a detection threshold. This is why brute force, fuzzing, and trial and error attacks are traditionally considered risky, not because they are slow, but because they are visible. The defender's advantage comes from observing failure first and responding before correctness is achieved. This assumption is deeply embedded across modern defensive architectures, from intrusion detection systems to SIEM correlation engines. What matters here is not whether the final input is valid, but how many invalid ones appear along the way. Security, in other words, relies less on preventing correct behavior and more on attackers being wrong often enough to reveal themselves. After a vulnerability is patched, most people assume the problem has been solved, but what really happens is that the attack surface is reduced, not removed. Input validation, filtering, and sanitization block the majority of malformed or obviously malicious inputs before they ever reach the execution layer, and that creates a sense of confidence that the system is now safe. What remains, however, is a narrow residual surface consisting of inputs that are still considered valid under the system's own rules. These inputs cross an implicit trust boundary, not because they are proven safe, but because they conform to expected structure, length, or syntax. From a defensive perspective, this is acceptable because the remaining space appears small and difficult to reach. From an attacker's perspective, that remaining space becomes a search problem. The vulnerability survives not as an obvious flaw, but as an assumption that anything passing validation must also be benign. Patching minimizes risk by shrinking the space of possible failures, but it does not eliminate the need for trust at the execution boundary. The critical point is that once an input crosses that boundary, it is treated as legitimate, and the system's defenses largely disengage. Security, at this stage, is no longer about blocking malicious behavior, but about whether the system has correctly identified where trust should and should not be applied. In a classical red team scenario, exploitation is rarely about executing a payload and almost always about surviving the process of getting there. The attacker is forced to search across parameters, encodings, command structures, and execution contexts, adjusting inputs incrementally based on how the target system responds. Each failed attempt produces observable artifacts, validation errors, malformed requests, anomalous input patterns, and log entries that accumulate over time. These failures are not incidental. They are the dominant cost of exploitation. Every incorrect guess increases the likelihood of detection, correlation, and response, long before a successful command ever executes. Defensive systems implicitly rely on this noise, using repetition and error frequency as signals of malicious intent. From the attacker's perspective, progress is slow and exposed, requiring repeated interaction with the target to refine inputs until a viable path is discovered. What matters here is that the exploitation process is visible precisely because it depends on being wrong many times. The true barrier is not the strength of the payload, but the number of mistakes required before correctness is achieved. In classical environments, exploitation is noisy by design, and that noise is what gives defenders their early warning advantage. What changes under a quantum threat model is not the vulnerability and not the payload, but the way an attacker learns. In a classical setting, finding a valid injection path requires sequential trial and error, with each failed attempt revealing a little more information at the cost of generating noise. On average, success emerges only after roughly half of the possible candidates have been tested, which means many observable failures before anything works. Quantum-assisted search changes this dynamic by compressing uncertainty. Instead of learning through repeated incorrect guesses, probability mass is amplified toward valid inputs, reducing the expected number of attempts from linear to square root scale. The attacker does not move faster in time, they move faster in certainty. This matters because defenders do not detect attacks by seeing success. They detect them by observing failure. When the number of failed attempts collapses, logs thin out, anomalies weaken, and correlation engines lose the signals they rely on for early warning. From the defender's perspective, the attack appears to arrive fully formed, without the preparatory noise that normally precedes compromise. The critical asymmetry here is informational. The attacker's confidence grows faster than the defender's ability to observe learning in progress. That gap is the real quantum advantage, and it exists entirely before encryption, authentication, or protocol logic are ever touched. What ultimately fails under a quantum threat model is not the exploit surface itself, but the detection logic that surrounds it. Classical defenses are built on the expectation that meaningful activity produces measurable noise. Repeated failures, elevated log volume, correlated anomalies, and sustained deviation from baseline behavior. In a classical attack, those signals accumulate gradually as an attacker explores the input space, and detection systems learn by observing that accumulation over time. When quantum-assisted search compresses the number of required attempts, that learning process collapses. Instead of a long sequence of failed inputs that rise toward a detection threshold, the system observes very little activity followed by apparent correctness. Log volume drops, anomaly scores remain low, and correlation engines see no sustained pattern to act on. The attacker does not evade detection by hiding success, but by removing the mistakes that detection depends on. From the defender's perspective, there is no gradual warning phase, no preparatory noise, and no meaningful signal to escalate. What remains is a narrow, high-confidence interaction that looks indistinguishable from legitimate behavior. This is why the risk is structural rather than tactical. Detection systems lose information before anything visibly goes wrong. When uncertainty is compressed, defenders are deprived of the data they rely on to recognize learning and progress, and by the time success is observable, the opportunity to intervene has already passed. The critical point to understand is that this failure occurs before cryptography ever becomes relevant. Encryption, protocols, and algorithms only activate after a system has already made a decision about what input is valid, trusted, and allowed to proceed. That decision layer determines whether data is interpreted as benign or rejected as invalid. And once an input crosses that boundary, downstream security mechanisms largely disengage. In the cases examined here, nothing about the encryption is broken. No protocol rules are violated and no algorithm behaves incorrectly. The system is functioning exactly as designed. The failure happens earlier, at the moment where structure is mistaken for safety and correctness is mistaken for trust. When quantum-assisted techniques reduce the number of incorrect decisions an attacker must make, defenders lose the opportunity to observe learning in progress. Failed inputs no longer accumulate, warning signals no longer rise gradually, and detection logic has nothing meaningful to act on. By the time encrypted channels, authenticated sessions, or protocol checks engage, the decisive error has already occurred. This is why the threat is pre-cryptographic. It exploits assumptions embedded in input handling and decision-making long before cryptographic guarantees are ever applied. Security does not fail because encryption is weak, but because trust is granted too early based on structure rather than intent. The central takeaway from this analysis is that quantum advantage does not arrive as a dramatic break, but as a quiet shift in how learning unfolds under uncertainty. When quantum techniques compress learning faster than observation is possible, defenders lose their primary source of early warning. The risk emerges before any encryption is challenged, before any protocol is violated, and before any algorithm behaves incorrectly. Detection logic depends on observing mistakes over time, on seeing errors accumulate, and on correlating noisy behavior into something actionable. When input errors are compressed in time, that logic collapses. What remains is not an obviously malicious sequence of events, but a narrow interaction that appears correct by every structural measure the system uses. This is why the threat is fundamentally pre-cryptographic and pre-protocol. Nothing downstream ever has a chance to intervene. Security systems lose data before anything visibly succeeds, and by the time success is observable, the opportunity for response has already passed. The lesson is not that quantum systems make attacks more powerful, but that they make attackers wrong fewer times, and it is that reduction in visible failure, not raw computational speed, that undermines the defensive assumptions modern security architectures are built upon. Thank you for watching. If you found this useful, please like the video and subscribe to the channel. It really helps us keep building deep, real-world quantum security content. You can visit spectreai.ai to explore over 55 hands-on quantum security labs and learn by doing, not just by theory. If you're interested in going deeper, you can also find our books on Amazon. And finally, leave a comment and let us know what you'd like to learn next. We read them all. Thanks again, and we'll see you in the next video.